Hi, a very good day to our lecture. Okay, today I would like to present about the subject, lab subject, which is thermodynamics lab. So the explain that we have done is heat conduction. So these are my group mates, which is Yuvneswari, Satyarao, Satishwari, and also Vijayavaraman. Okay, next about the introduction. So first about the heat conduction. So heat conduction is occurs in the three-dimensional practice, and which is difficult problem that necessitates a great deal of the computation. However, the major part of the one-dimensional heat transfer is problem to encounter the practice and the app and can be approached immediately. And a one-dimensional approach is required to demonstrate the fundamental law that relates heat flow rate, temperature gradient, and also the area. So here the picture shows about the heat conduction through the large plane wall. So in this picture shows the T equals to T2 minus T1, which is the temperature difference across the wall, and the heat conduction to the large plane wall, which thickness is X, which is L, and also area is A. The rate of the heat conduction of the plane layer is proportional to the temperature difference across the layer and also heat transfer area, but inversely proportional to the layer thickness. So now I want to tell about the linear conduction heat transfer. So here the picture shows the temperature gradient dt dx is simply the slope of the temperature curve on the tx diagram. So here the q dot more than the zero heat flow. So here the linear conduction of the heat transfer is a Fourier law of the heat conduction. For one-dimensional heat conduction, express the rate of heat conduction through the medium in a given direction. So the positive x direction, the temperature gradient is negative since the heat conducts in the direction of the decreasing temperature.
A very good day, I bid to the lecturer. My name is Satishwaran, metric number MA18054, and I would like to present about the experimental apparatus for the heat conduction lab. Okay, moving on to the first part will be the experimental apparatus informations. The equipment's comparisons of two heat conducting specimens, a multi-section bars of examinations of a linear conduction, and also the metal disc of the radial conduction. To the second one, with the control panel was being provided for an electrical and power digital for the display heater in the all the specimen, as well as the selector switch for the data for the acquisition system. And the third one will be a small flow of cooling water provides a heat sink and the end of the conducting part in each of the specimens. There are almost 11 main experimental materials that have been implemented in the machine. For the first one with the control panel, which is the box of the heat conduction system, and second with the heat power indicator. The heat power indicator has been displayed through the panel control panel box, and also the heat power regulator, which we can adjust from the 0 to the frequency of 100 kilos. To the fourth one will be the heat power connector, which we can connect and also eject the source of the power connector. And the fifth will be the temperature indicator, which indicates the temperature reading throughout the experiment. And for the sixth will be the temperature selector. Okay, for the temperature selector, we can eventually select our temperature from 0 to the 100 degrees Celsius. And also number 7 will be the main power switch, where it is the main switch for the whole system to operate and also to close the system. And for the 8 would be the temperature sensor wires. And for the 9 will be the DAS signal selector. And 10 and 11 is radial module and linear module, which these are the most 11 components that is being specified as an experimental for the materials. Moving on to the next part will be the procedures. Okay, for the procedures, we having two types of experiment. One will be linear module, and another one more will be the different one. So for the linear module, we'll be make sure the current main switch is turned off. First step is to turn off the switch. And moving on to the next part will be the linear module, where it's been clamped together after the brass conductor 25 diameter section intermediate section was inserted. Okay, for the second procedure of the experiment will be the water supply was turned on, and also the water flow of from the free end of the water pipe to drain. Okay. The third will be the heat power connector knob was fully anti-clockwise turned, which has been the heat power connector knob was been anti-clockwise turned for the sensor to be connected as well to the power supply, and the main switch has been turned on for the system to be run in the read out will be the eliminated. To the next part will be the software of the heat conduction was loaded. Okay. The next part will be the heat power control was set to 5 volt, and the enough time was allowed for steady state condition to be reached before recording the temperature at all the 6 sensors point and the input power reading of the voltmeter too. And the data was saved and also been recorded. To the next part of the experiment will be the linear module, the experiment B. In the experiment B, the linear module, the brass section was then removed, and a stainless steel section with the same diameter of 25 diameter was inserted to the test area, and the steps 2 to 5 were repeated where all the clockwise turn and also the drainage of the water has been repeatedly done here. And to the next one be the control. The knob was turned from the 10 volt to the 15 volt respectively, and the temperature was recorded as described above. And finally, the heater was turned off, but the water supply was kept running until the water was being kept cool for any damages to the user or the machine. That's all from me. Thank you.
Hello, my name is Vijayvarman Ramesh. My metric ID is MA18251. I will be presenting the result and calculation for heat conduction lab report. So for the experimental data, we have two specimens, which is stainless steel and brass with a 25mm diameter. So the experiment is carried out to find out the temperature at each measuring point with 7 different locations. So the manipulative variable was the heater power. So for stainless steel, we had 3 heater power, which is 5 watts, 10 watts and 15 watts, and then the temperature at each measuring point was recorded. And then for brass, we have only 1 heater power, which is 5 watts, and then the measuring temperature measuring at each point is tabulated. So for 5 watt stainless steel specimen, we have the graph for each of them. So this is for the 5 watt stainless steel, and then 10 watt stainless steel, and then 15 watts stainless steel. What was the difference is the heater power increases, the temperature increases. As you can see, the graph of stainless steel from 5 to 15 watts, it remains, the shape remains same, but then the value of temperature is increasing. So this is for the 5 watt brass temperature versus location graph. Next, for calculations, we had the diameter of all specimen, which is d equals to 0.025 meter. So using the area formula, which is pi d square over 4, we get the area, and then the del t over del x is the gradient from the graph we did before. So we simply take 0.3 to 7 to calculate the thermal conductivity. So for stainless steel 5 watts, we get the gradient from the graph, and then using the heat conduction formula, which is Ka times del T over del X, we get the thermal conductivity for 5 watts heater power, which is 122.25 watts per meter degree Celsius. So the same thing has been done for all the calculations. We get the gradient from the graph, and then using the heat conduction formula, we get thermal conductivity for 10 watts heater power, which is 202.84 watts per meter degree Celsius, and for 15 watts heater power, we get the thermal conductivity, that is 297.62 watts per meter degree Celsius. And then for brass 5 watts, it is the same solution. So we get the thermal conductivity is 100.30 watts per meter degree Celsius. That's all from me. My friends will continue after this. Thank you.
Hi everyone, I'm Yuneshwari. Let me start with the discussion. Firstly, on comparison of calculated thermal conductivity to its typical value. Heat flows radially outwards from the center in radial heat conduction. Since the area of successive layers increase with radius, the temperature gradient must decrease with radius, which shows a small variation in temperature between points but a nearly constant rate. Next, system of heat conduction in this experiment requires cooling rate flow. Cooling can be crucial in industrial application to ensure that process do not overheat the equipment or product because water has a high boiling point and a specific heat. It is used as a medium to absorb heat in many cooling applications. Next, reason why thermal conductivity value for particular material is important in engineering is to identify the significance of material thermal conductivity in each thermal management application. This is also to measure the internal thermal resistance of a heat sink as heat travels from the base to fins and dissipates in the environment. Heat insulation method has been used in engineering nowadays. The main three usage is on mineral wool, PVC foam and insulation. Mineral wool is an insulation material made from natural or synthetic fibers such as slag and ceramics. PVC has introduced heat insulator PVC panels for ceilings and wall. Insulation is used for piping system. Lastly, on conclusion, the experiment that was carried out was a success. Thermal conduction occurs when heat is transferred from a higher temperature region to a lower temperature. As a result, the higher the temperature, the nearer the material receives the heat. The thermal conductivity of steel and brass was determined with brass having a greater thermal conductivity than steel. Brass has higher thermal conductivity in radial flow than in linear flow from different flow rate. That's all from us. Thank you.